Our next example is a delta source with delta load with line impedance. So here I have a three-phase delta connection, and always I'm going to use the positive phase sequence ABC. Now this line has an impedance and the load is also a delta load. Okay, this is a positive phase sequence, so A, B, C, positive phase sequence, clockwise direction. Okay, so and it is symmetrical load. You mentioned the load impedance is 12 minus J9. Let me verify one more time before we proceed. Yes. Okay, 12 minus J9. On the line impedance we have 1 plus J1 ohm, and the phase voltage he gave us 120 at an angle of 0. Okay, remember in delta phase voltage is equal to line voltage. At the same time phase current or line current equal to √3 times phase current, and the line current always lags 30 degrees, so it's minus 30 with the phase. Sometimes you don't need to use the angles, but if you need to draw a vector diagram, it's a good idea to use the angles. Okay, it's a symmetrical load, so each phase has the same amount of impedance. Okay, if we don't have a line impedance, then it's easy to solve because the phase voltage here same as the phase voltage at the load. But in this case, what happens, since we have a line impedance, there is a voltage drop. There is a voltage drop in the line. We don't know what is that voltage drop is. So the best way to solve this example is we need to convert that given load into a star. So if we convert given load into a star, this is how it's going to be look like. Okay, so this is impedance, phase A impedance, ZA. Okay, so when you convert star into a delta, your delta into star, ZA equal to, remember always delta values are larger than star values, so your star impedance is since it's a symmetrical load, it's just 12 minus J9 divided by 3, which is 4 minus J3 ohms. Okay, so I'm going to redraw the circuit with load impedance. By the way, the question he's asking about what is the power consumed in the load, and active power, reactive power consumed in the load, and apparent power, cos theta load power factor, cos theta of load, and cos theta of source, and line losses. And line losses. That's what he's asking for. So what I'm going to do, I'm going to redraw a circuit with a delta source with a star load. Okay, so here is my A, B, and C. That's small a, small b, small c. So this is 4 minus J3, 1 plus J1. Okay, now here this is a line voltage as well as phase voltage, which is 120 at an angle of 0. Okay, now since these two, the line impedance as well as the impedance of that phase, they are in series, so we can add them. If we add them, we're going to add the resistor values, but subtract the reactance values. A, B, C, A, B, C. Since the one is inductive reactance and one is capacitive reactance, so this is 5 minus J2. Okay, so that's the total impedance looking from the source side. If you look at, cos theta of load equal to, this is R load over Z load. R load we have 4 and Z load 4 square plus 3 square, which is 5. So 4 over 5, which is 0.8. Since it's a capacitive load, leading power factor. Okay, same way cos theta of source. When we look at the source point of view, this is R total over Z total. We have R total as 5 ohms and Z total square root of 5 square plus 2 square. Okay, that value is I have the load power factor. Okay, it's 0.928. Still it is leading. So we have two different power factor. So load power factor is 0.8. When we look at it source point of view, it's 0.928 leading. Okay, unity power factor is always good. So as long as it's close to unity power factor, that's good. Now if you look at the circuit diagram, now the line to line voltage we have, so if you look at VAB, this is VAB, that VAB, we have VAB equal to 120 at an angle of 0. This is phase voltage on the source side, on the source side. But when we look at this from the load side, that 120 is the line voltage. So VAB equal to 120 at an angle of 0, which is line voltage only from the load side. So from the load point of view, VAB equal to 120 at an angle of 0, that's a line voltage. So it's a star connection. So to get the phase voltage, VAN equal to 120 over square root 3 at an angle of minus 30, because phase voltage on the, there is a 30 degrees angle between the phase voltage and line voltage. Line voltage always leads in star connection with the phase voltage. Okay, so that's the reason minus 30. Okay, so we have that value. I have 69 something. Give me a second. I have that as 69.28 at an angle of minus 30 degrees. Now if you look at the load impedance, so we have the load impedance, this is 5 minus J2, and the voltage across this as 69.28 at an angle of minus 30 degrees. Okay, so the phase current IPH, which is the load phase current, equal to 69.28 over 5 minus J2. Okay, so VPH over impedance ZPH. Okay, so the phase current I have 12.86 at an angle of minus 8.19. If you look at the angles, I didn't put the angle here. The angle here is minus 30, and you will end up with some more angle there. Okay, so the angle between the phase voltage and phase current is only I mean the phase voltage and phase current is around, I don't know, minus 30 plus whatever that angle you will end up with here. That angle is 21.8. Okay, so basically this is 69.28 at an angle of minus 30 divided by 5.38 when I convert that rectangular format into polar format, minus 21.8. That's how I end up with that angle. Okay, so that's the phase current. Once I have the phase values, P source, because when we look at here, okay, what is the source power, okay, and we can find the load later on. So the source power equal to 3 times VPH IPH cos theta of source. So we have 3 times VPH is 69.28, IPH is 12.86, and cos theta is 0.9, whatever we have here, it is 0.928. That is the source power, which is 2481.729 watts or watt. Okay, and P line losses. So if you look at the line losses, so if you look at this, the current passing through this is 12.86. That's the current passing through this. So the line current here is 12.86, and the line losses are 3 times IPH square times R line, which is 3 times the IPH we have is 12.86 whole square times R line is 1. Okay, so the line losses I have 496.13 watts. Okay, 496.13 watts. Those are the power line losses. And okay, so same way we'll find S source. This is the apparent power of source, so that's a 3 times VPH IPH. So all you need to do is just multiply it by that. So 3 times 69.28 or 12.86 will end up with sorry, I didn't do this calculation before, but I'll do it right now. Okay, so I have 3 times 69.28 times 12.86. Okay, that is 2672.82 volt ampere. Okay, and Q source must be square root of S source minus P source whole square. Okay, so square root of 2672 whole square minus 2481.72 whole square. So 2672.8 whole square minus 2481. That value is 992.49. That's the reactive power supplied by the source. Okay, now okay, can we find Q Q line? Q line is same as 3 times IP or IL square. In this case IPH and IL are same because of the star connected load. XL, so 3 times 12.86 times 1 will end up with 496.13 volt ampere reactive. Okay, this is volt ampere reactive. Okay, so Q load is, okay, remember this Q line, it is consuming, and the Q source load is supplying it back. So the total is going to be 992.49 plus 496.13. That's the total reactive power generated by the load. So in this case, load is generating since it is capacitive load. Okay, this value is 1488.62 volt ampere reactive. Okay, so we have PQ as source as well as load. What else he is asking for? Cos theta of load, line losses, we have everything in this example. Okay, thank you.